What if we want just a normal alkyl group to be our nucleophile? Say CH3 minus, right? There is no such thing as CH3 minus in a bottle that I can make or buy and then use, right? The closest thing we have to CH3 minus, and it's pretty close, is the Grignard reagent. So we talked about the Grignard reagents and alkyl lithiums before. These are really, really powerful bases, and they're really powerful nucleophiles. Earlier, I said that they're too basic to be effective in SN2 reactions. However, they work a lot better when it comes to carbonyl attack. As a reminder, we get these Grignard reagents by taking some alkyl bromide and reacting it with magnesium metal. So we buy shavings, like little bits of magnesium metal, and if you put them in a flask with some alkyl bromide, you'll actually see those little bits of metal look like they start to dissolve, which is crazy because magnesium does not dissolve in water at all, right? It's a really stiff, hard metal. But this will kind of eat away at that magnesium really, really quickly and actually spit out a lot of heat in doing so. This is a really exothermic reaction. But that gives us a Grignard reagent. We can also just buy the Grignard reagent. And this is another example of what is essentially a very high energy sigma bond. So this high energy sigma bond is our nucleophile. This ketone is our electrophile. My electrons come in there. Electrons go on to oxygen. And I end up with this alcohol. There's no leaving group because now I've got 3 alkyl groups, none of which can leave. And so it basically sits here until I give it some weak acid. Again, this is a vague way to write acid, but aqueous ammonium chloride would be another good choice here. And this is a great way to get to tertiary alcohol. So ketone to tertiary alcohol works just great. We can also think of the same process with aldehydes and either Grignards or alkyl lithium. So for instance, if I give this butyl lithium, which I said is a really common base and nucleophile that we use in the lab, this is a really nice way to make secondary alcohols. Now you might have noticed I used ether as my solvent in both of these cases. Why is that? Well, there's actually some pretty technical reasons why ether is good at dealing with magnesium and lithium reactions. It has to do with how the lithium binds to the oxygen in ether. But the bigger point to make is that I can't use any acidic solvents. And by acidic, I don't mean just acetic acid or sulfuric acid or something. By acidic, I mean water. So these things, both Grignard reagents and alkyl lithiums, are so basic that before they do any of this stuff, they're going to scrounge your entire flask for any little bits of water they can find. All right, and if you're doing a small scale reaction and your glassware is just a little bit moist, or a little bit of water on the glass that you can't even see, that will kill your reaction because this will react with water in an acid-base reaction way faster than anything else. Remember, acid-base reactions are essentially faster than just about any other reaction that we talk about in this class. Grignard reagents, alkyl lithiums, fantastic nucleophiles, really good ways to make new alcohols, but also make new carbon-carbon bonds. It's really important to be able to make new carbon-carbon bonds if we're trying to make anything of any complexity. So these are great reactions to know. We're going to have to be careful, though, that there are no acidic solvents or really anything else that's acidic even in the molecule, right? If I had an OH hanging off of here, I'd be dead in the water before I started because it would just deprotonate my OH and not do the reaction that I wanted it to do. Okay, so we have to be careful. No acidic protons either in the reactant or in the solvent or on the glassware or in the air over the flask, any of that stuff. But if we're careful and we keep it dry, then we will make a new carbon-carbon bond with very high yield.